Voy a esperar a que inicie la grabación. Ok, muy bien. Buenas tardes a todos, bienvenidos a la presentación de John Alejandro Montañez Barrera, que nos presentará los avances de su trabajo de doctorado en este seminario de Ingeniería Mecánica de la DISIS-UG. Adelante, John.
Bueno, un saludo a todos. Primero, darle las gracias a mis asesores por asistir. Voy a dar la charla en inglés porque uno de mis asesores, pues, su lengua materna es en inglés. Entonces, pues, espero que les sea de su agrado. Well, I'm going to talk about the Steepest-Entropy-Ascent quantum thermodynamics, modeling of noise intermediate scale quantum devices. Well, okay. The outline of this work, first I'm going to do an introduction. I'm going to talk a little bit about what is the quantum computer overview, the problem related with decoherence, that is the main topic of this project. A little bit about the Limland framework, the Steepest-Entropy-Ascent quantum thermodynamics framework, the objective of this work, the results of the dissipative theories on NISQ devices. Here we use the SEAQT framework and the Limland to make some predictions in quantum computers. One of them is the decoherence in quantum dots. The other is the coherence in some superconducting qubits. Finally, we present a method for generating random perturbed density operators in these devices. The future work, or the work that we have for this remaining period, and the conclusions of this project. Okay, first the introduction. Well, quantum computing exploits two principal phenomena from quantum mechanics. One is called superposition. When we have this quantum analog to the classical information, or how we store classical information, that is in bits. Well, for quantum mechanics or for quantum computation, we have or we can extrapolate this to a qubit, that is our quantum information, how quantum information is stored. At least we have two levels, 0 and 1, but we have all the set of values between 0 and 1, and this can be represented by a block sphere. That is like a sphere with radius equal to 1, and here we represent, instead of defining 0 or 1, we define with probabilities if we are in 0 and 1. And entanglement is a correlation between different subsystems or different qubits. And the most representative case is the Bell state. And what we have here, and this comes from the superposition. First, if we have an state in superposition, we can create this correlation between an state in superposition and another system. And we create this with a Hamadar gate. Here is the representation of a quantum circuit when we have this like a set of gates equally of what we can find in classical computers, but with some special abilities. And this is a control node, which means that if the control qubit, that in this case is this bullet here, is in 0, the second is going to be in 0, but if this is in 1, the second is going to be in 1, or we change the state of the second qubit. And this is the representation of my state. And the entanglement or the correlation that we create is that now if I have a 0 in one of the qubits, the other is going to be in 0. And the same if I have a 1, I'm going to have a 1. And this is the main two phenomena that describe a quantum computer. we can extend this using other relations, but the main two phenomena are these. Okay, a little bit about what is the story of quantum computation. This started in 1981 with a MIT conference that is really famous in the quantum community, because here Richard Feynman gave a talk saying that if we want to simulate or to extract information for quantum systems, we need quantum computers or quantum systems simulating the phenomena of quantum mechanics. And it's something that we cannot skip, because the complexity in classical computer to simulate a molecule grows exponentially with the number of particles. Then it's important because this is the starting point, and after that came with a lot of results in quantum computing and quantum information. And in 1994, we have the Shor's algorithm, and this is one of the most famous algorithms in quantum computation, because this allows to solve an NP-hard problem that is known as finding the prime numbers that, if I have a number n, what are the prime numbers that compose that number? And cryptography and how we hide information, or how we can use cryptography, is based on this principle that the complexity grows exponentially. And in 1996, we also have another of the classical algorithms in quantum computation that is called the Grovers. And this is if we have a list of instructor items, how we can find one item there. And was shown that this can be solved with quantum computers in a time that grows at least with the square root of n, then is surpass what classical computers can do, and can be used this has many applications, as well as the Shor's algorithm. In 2001, we have the first simulation of one of these algorithms, that is the Shor's algorithm, in a 7-qubit nuclear magnetic resonance. Here, even though that was just factoring the number 15 into its prime cofactors, that is 5 and 3, was the first realization of a quantum algorithm in a quantum computer, that is in nuclear magnetic resonance quantum computer. In 2007 comes one of the first NISQ devices. When refers to NISQ, is because this has noise, and they are in intermediate scale, because the number of qubits doesn't grow over 100 qubits. That is the unit of information. But is one of the first realization of a useful quantum computer that can be scaled, and was developed in 2007. And most recently came two quantum algorithms that works in this NISQ era. There are the quantum approximation optimization algorithm and the variational quantum eigensolver. Both use the ability of or the possibility to codify a problem, NP problem, into a Hamiltonian of a quantum system, and we can use this to solve combinatorial problems. For the case of the QAOA, or for the VQE, we can solve the ground state of chemical molecules. And most recently, in 2016, IBM put the first processor on the cloud. This is a really big step, because this opened quantum computation to the whole community. We now have access to these devices as the public. Also, they have a research program in which I am. that allows to use some of the computers. Here we can see the representation of one of them. The whole bunch of like circuits here are mainly to refrigerate the quantum processor that is in the bottom of this like device. And yeah, it's because these have to be 15 millikelvin to work, or is the operational temperature. And in 2019, we have some of the big announcements from Google. They made a quantum circuit that requires classical computer 10,000 years for the most complex circuit that they create. They calculate that a classical computer or a supercomputer from what we have now take at least 1,000 years to execute the same circuit of something that the SEAQT, that is the device that they made with 54 qubits, takes is a question of minutes, and they call that quantum supremacy. That is a term that tried to say that a quantum computer overpass what a classical computer can do. And the application goes from chemistry. As I told, these variational quantum algorithms work with these models. And also we have in healthcare to accelerate diagnosis, personalized medicine, and optimize pricing. This comes from two main areas of research in quantum computer. One of them is the optimization, or these variational quantum algorithms that makes optimization, we can say that faster than classical computer. And in biology, with protein design, material science, if you can encode a material into an Ising model, you can simulate this in quantum devices. Also in finance, with optimization, and in machine learning with models that represent quantum neural networks. Then yeah, there are a lot of applications now, but we are centered now in the NISQ era of quantum computing. We have two different devices, and I'm just highlighting them they here because is what I've been using. One is the superconducting qubit, or the Trasmon qubit that I just mentioned from IBM. They only works with this technology, and it's like kind of a non-harmonic oscillator. Then if we see the representation on the left, this is a circuit that is a capacitor and an inductor. And this can be represented by a quantum harmonic oscillator. But if we replace the inductor for a Joseph subjunction, that is two superconducting materials, and in the middle an insulator, we can create an harmonic oscillator, which means that the separation of the eigenlevels is different from the first from the transition from 0 to 1, that from 1 to 2, and we can restrict our system to work between 0 and 1, and then we have a qubit. And the quantum dots are electrical particles that we confine in some part of the circuit, and we can control them applying a voltage. And then pairs of dots makes a qubit, and we can control them and create a quantum qubit. A little about the quantum computing companies. We have like here, I show not all of them. I am showing just the most representative of what I've been working with. One of them is IBM, is my principal source of experiments. I am doing all my work, almost all my work on this technology. I can execute my code and send to a real quantum device and get the result back. And because I am doing this research program at IBM, I have access to other devices at pulse level. Then I have the whole control of the system. We have also Xanadu. This is mainly interest in quantum machine learning, but they design its own device based on photonics. We have Rigetti that works also with Trasmon qubits. We have the wave that is a different kind of technology because it's not whole purpose. Then we cannot create a whole circuit, but we can storage the Hamiltonian and we can apply a quantum annealer to find the ground state. Then this is something useful in quantum if we want to do optimization, because we can create our problem or translate our problem into what is known as quadratic unconstrained binary optimization, and use this technology that has 2,000 qubits to solve our problems. Then, yeah, we can make good solutions here, and there are a lot of companies interested in optimization. Then this is one of the biggest. IonQ works with ions. They like trap the ions or particles, and those particles are the qubits. And this is a good technology because the noise is low in comparison with others like IBM Trasmon qubits. But the problem with this is the scalability. There is not, we cannot say in this moment that this is going to be something that is going to be a scale, could be a scale, but yeah, it's a good technology and is some development there. And we have Google. Also, they have cloud access to the Sycamore device, but yeah, they prefer to work like independently. Yeah, IBM is more open to the community. Okay, and here I want to put this perspective of at least what IBM want to do for the next couple years, and in 2023 they are going to surpass the 1,000 qubits, and it's really good because at least what the predictions are of what quantum computing can really have a practical applications that surpass whatever supercomputer is with 400 qubits and the QAOA algorithm. Then our real applications are going to, when we surpass that limit. Then maybe next year we are going to see if the practical applications of quantum computing. And the market, that is the last one of this review of the quantum computing companies, mainly are going to focus on cloud access. And I think that is the target, having all this technology from Google, from IBM, from Intel or Amazon that are working on this. They are going to present all of this in the cloud. And for by 2026 is going to be a market of more than $2.2 billion. Well, but the problem with Decoherence is that we have two main phenomena, and they describe always this in T1 and T2 times when they prove a device. And they always give these numbers because it's a measurement that is inherent to the system. Then you are going to have some oscillation of these numbers, but almost are going to be in the same range. For T1 is the relaxation, how it takes a system to lose the information that is stored in the C direction. because when we interact with the environment, the system loses this information from the 1 to 0 state that is like associated with the energy of the system. Then yeah, we are losing the energy of the system because the interaction with the environment. Then we have a representation by T1 of the relaxation phenomenon. And the second is the phasing, that is that we lose the information stored in the XY plane. And here you at the left, you can see that this circle, that is what I should observe if I have an ideal system. But the reality is that I am losing information. Um, Sometimes is referred like a perturbation of the system, but I'm going to explain more in detail when I explain the SEAQT framework. We believe that this is inherent to the system when the system is in a non-equilibrium state. Then this is the evolution that we expect when we have a quantum device. Then we are losing information here. We want to explain why we lose this information. And in any case, if we can come with a solution or at least to predict and apply error mitigation techniques, this will be really good for the quantum computing community. Before jumping into the frameworks that try to explain both phenomena that I just mentioned, we have the Hamiltonian, that is the energy of the system, how we present this energy, and is the sum of the kinetic and the potential energy. We have the dot product. When we have this hat, is because it's a matrix, and we have here the trace, that is the sum of the main diagonal of the elements. And we have the dagger, that is the complex conjugate transpose of a matrix. And this is important because like kind of we can represent this as a vector. Then if we take the dot product, we have the magnitude of that in some direction. Okay, and the density operator is how we represent the qubit, how we represent this block sphere and where we are. For example, we are here, we have a way to represent this in ways of a matrix representation. We have the magnitude as Rx, Rx, Ry, and Rc. And the sigma x, sigma y, and sigma z are the Pauli matrices that allows me to represent in 3 directions my system, at least for 1 qubit, that this is here. For 2 qubits is different, but yeah. And now, how the coherence can be explained? Well, ideally, we should only have this first part. And we describe here how the density operator evolves through time, and is based only on the Hamiltonian. But once the system interacts with the environment, we add these terms. It's a dissipative terms that means the loss of information of my system, my qubit, for example. And here we have the Limland equation. This is a term that comes from the Limland representations. And here what we have is that my system is interacting weakly with an environment. And from that perspective, we can come with this dissipative term. When gamma is the I is the exponential or spontaneous decay rate, and the operator, here we have to select the operator based on the phenomena that we have in our evolution. For example, if we have relaxation, we use the annihilator operator called L1 here. And for the phasing, that is the phasing here, we have the sigma C rotation. Then this is a representation of the how is the evolution of a system. We have our operators here. This is yeah, the representation, and here we have an anti-commutator that is just some operation in matrix basis. Okay, and what are more interesting in is to show if the steepest entropy ascent principle can be fit into NISQ devices. And this is important because this is a different framework, not consider only the weak interaction between a system and a reservoir. Is more than a system inherently, when it's out of equilibrium, evolves to an equilibrium state, but following a path of maximal entropy production. Then and this is this come from Gianpaolo Beretta in 1981. He presented a paper when he showed these principles, and is based also in other works from Distopoulos and Hastopoulos, and recently working with Dr. Michael von Spakovsky. But this principle say that the evolution follow this the derivative of the entropy, in this case the entropy that includes to all the needed properties of the entropy is the von Neumann entropy. Then if we follow that formula, we can come with a dissipative term that explains how the system evolves. But if we only take the entropy, we have this vector, and the green part here represents the Hamiltonian of the energy of the system, and because we are basing this on a closed system, we should consider the energy constant. Then we have to extract, this is a dot product, the part of the Hamiltonian that has this vector, and the other is the direction of the square root of rho, and only take this part that is the dissipative term in that direction, which is present here the perpendicular to those generators of motion, that is the identity and the Hamiltonian, and with that we can construct the density operator. But more in detail, because yeah, formulas are not telling much, but if we can extrapolate what happens there. Here we have the equation of motion for different subsystems, where J represents subsystem 0, subsystem 1, different subsystem that could be represent qubit 0, qubit 1, qubit 2, and tau d is the dissipative time, and this measure how quick my system is losing information from the perspective of the SEAQT equation of motion. And yeah, here is what happens. If we follow only the ideal case, we should have a circle here, this evolution, because my Hamiltonian is pointing in the z direction, then this is a rotation around the z-axis, about the z-axis. But because of the dissipation, we are going to the center of this, because this is the path of maximal entropy production. And here we can see how is the entropy and the entropy generation acting of this example. And here we have that we are going to the maximal entropy production, never reaching that point, but always decreasing the entropy generation, that is the derivative of the entropy. And yeah, that's the evolution of our system in this special case, and the dissipative term acts in that way. Well, the objectives of this work is first apply both equations to NISQ devices to see if they can answer answer what happened with the noise in these devices and using the SEAQT framework. And what if we can mitigate that error based on the equation or the SEAQT framework? The results, this is a paper that we already published. We are based on some experiment from Schulman in 2012. They published that on Science, and they come with these double quantum dots that represent a 2-qubit system where they can vary the voltage. Here is represent with epsilon, and they have a sequence of pulses. We can refer this if we apply a voltage as a pulse, and if we apply a magnetic field, also we can have a pulse. Then the Hamiltonian is described by this expression when the term important here is the coupling factor that makes this control phase rotation. That is, as I show at the beginning of this presentation, is like the C-node gate, but instead of just turning 0 or 1, turning in the equator or in the XY direction, and controlled by one of the qubits. And we show that with the SEAQT equation of motion, we have these results. First, in the left, I show the fidelity. The fidelity shows if my system is in the state that I want. If it's a 1, is that I am in the state that I want, that is this state after the control phase gate, or not. And based on the von Neumann equation, or the ideal case that I show before, that is without this dissipation term, we don't have dissipation. We can observe this here. It's always keeping the same amplitude. But in terms of the SEAQT equation and the Limland, we observe some, that we can predict the experiments, and is in terms of dissipation. And on the right, I have the concurrence, that is the difference between eigenvalues, but taking the first eigenvalue as the maximum eigenvalue, and a value above 0 is represent that I have entanglement. That is what I expect. And again, here we show that with both theories, we can predict what happened with both frameworks. We can predict what happened with the experiments. And the thing is that we are losing information here, but it's really fast because we have that in a time of less than 200 nanoseconds, we lose the information. Then, we need to think about how to prevent this to happen, because we need more time to do the set of or the sequence of gates that we want in quantum computation. And here is another representation, is quite similar to the last. Also present the fidelity, but for different values of the different in voltage. Then from minus 20 microvolts to 100 microvolts. And here, this is really interesting because we found a relation between the dissipative time of the SEAQT equation of motion in terms of the entanglement time. The entanglement time is the where I find the peak of the entanglement. Because for the fidelity, the maximum entanglement for the experiment is the point of maximum fidelity. And this helps us to think about how to prevent, or what is the best configuration to work with to reduce the noise for this controlled phase gate. And here are some results of the Steepest-Entropy-Ascent quantum thermodynamics entropy. And here we have like a set of entropy, how is acting the entropy. We want to reduce the entropy. And here we can find some clues of how do this. For example, this in this part of the evolution for minus 20 microvolts, we see that we have this part that is plain, and we can find here what is the best point. For example, is just one of the example, and here is for the Lindblad. Yeah, and we cannot extract much from here in terms of entropy because, yeah, it's kind of, yeah, we cannot extract information from there. And the second paper that we are working on have almost all the results. We, instead of using experiment from someone else, we are using our own experiments. We use quantum device that is called IBM Q Bogota. This is a real device with 5 qubits, a quantum volume of 32. This is quantum volume is a measurement of how good is the quantum device. Lately we have something with 512, I think, at IBM. And with average T1 time, this T1 time I just mentioned, that is the relaxation, and T2 is related with the phasing. And we restrict this to work in 0 and 1 state, and we made 3 different experiments. Here is a representation. It's not the same as what we have here, but this is how I represent a quantum computer from IBM. Here we have the qubits. These lines are how we measure them, and these other resonator buses are the connection between qubits. And it's good because it's a representation of what we have. And T1 experiment, well, we start from 0. We apply this, that is a pulse in the qubit, and this turns to 1, the state. And from there, we leave the system to evolve throughout time. And we measure the C component because, yeah, it's what takes going from 1 to 0 again. And this is what we observe from the experiment of this device for both qubits. And yeah, here, Dr. Michael and one of his students, Tyler, made some derive this formula for when we have relaxation, because as the SEAQT framework is only for the phasing, but relaxation is not something that we can add if we don't consider that the system is interacting with an environment. Then they made this derivation and works really well to predict what happened with relaxation. And they include the temperature of the system. This is the inverse one of the Boltzmann constant times the temperature. Here we are working at 15 millikelvin, and here is the energy of the system. And with this modification, we can work in the relaxation phenomena. And the T2 experiment, I haven't showed the X component. I have the result, but I have to make some modification. But the sequence is like this. These are pulses, the pulses that represent our rotation. Here we rotate from 0 to the X position, leave the system to evolve throughout time, make pi rotation. This is to reduce some noise inside the system, and after we measure again, and we make another rotation and measure what happens. Here, this like this pink color represents the measurement of the system. Okay, and we did 2-qubit experiments when we try to show how the fidelity works when we change the width of the cross-resonant pulse. This cross-resonance is related with the C-node gate. We modified that cross-resonance pulse width, and we made those experiments. Here, here the time refers to the width of those pulses and how concurrence works in these devices. At least we can go a time to 20 microseconds. If you remember, we have less than 1 microsecond in the quantum dot, even though that's an experiment from 2012. But this can we surpass that that limit, and even at 20 microseconds, we still have some entanglement there. And the fidelity is like this, and it's acting like this. And again, this is experimentally. I have to make all of these experiments. For each of these points, I ran 8,000 individual shots or experiments, and yeah, and also 9 different circuits. Then it's 9 times 8,000 just for one point. And all of this through the cloud. And yeah, they have a library called SEAQT in Python, and we can connect to this system. Only ones have to register, and we can execute this. Well, and that's the part of the NISQ devices that we just try to explore if we can represent this with the SEAQT framework or not. But the reality is that yes, we can, and give good result, and it's a different approach to the same problem, but with a deeper phenomenological, because we include here the thermodynamics point of view. And after that, we make other project, and this is something that we need because the reality is that qubits, or the state of the qubits, are not ideal. Then we have states perturbed, and we need to work with these states perturbed with the SEAQT equation of motion and with the Lindblad equation. Then we came with this derivation, or Dr. Michael and Tyler, and I made some contribution in the part of using this for NISQ devices. And the thing is, we have an state. This is a Bell diagonal state, and if we want to perturb this to represent a different, to have a perturbed state, we can make this transition where gamma 0 is just the square root of gamma. Then we have this that is our perturbed state, and is based on eta ij. This eta ij we take as normal distributions with some mean and some standard deviation, and we apply some restrictions. If we want to work in some specific area or point, we can make this restriction of well, we can make, first we need to make the restrictions in the unitary trace, because this is related with the probability, and the probability couldn't sum more than 1. Then we need one there. That's the first restriction. But we can restrict in terms of energy and in terms of entropy, and create a perturbed state that correspond to that energy and that entropy. And is what we present here. We have 1,000 different shots for each of the constraints. The first constraint is just the unitary trace. The second constraint is the unitary trace and the energy. The third is the entropy and the unitary trace. And the fourth, C1, C2, and C3 is the energy, entropy, and energy, and unitary trace, sorry. And the baseline is the state, or my row 0 state. And we can create this bunch of points, and depends, We ensure that this follows the restriction that I am assuming. And here again with the energy. And this is really good because we present an application of this in the NISQ devices. We simulate a device that is called IBM Q Manila. We did some experiments here. We extract 2,200 points and or repeat this experiment 200 times. And yeah, here I present those results where my states are, even though that should be here in the baseline, they are here because they are NISQ devices and we have noise, and we can represent that noise with this perturbation method. And once we have these states, we extract the eta ij values that I mentioned that makes the perturbation, and simulate with based on that these states. And the thing is, like, if we select all the three constraints, we are really close to what is the real device. And these have not only applications like in simulations, but we can extract other properties from the eta ij values. And for characterization could be a really nice technique. Then yeah, we are working on other paper on this. And the future work is using these random perturbed states to with the SEAQT equation of motion to see how evolve them, and if we can predict we can predict some other experiment that we are working on. Conclusions. Well, first is that yeah, with the SEAQT framework, we can simulate what happened with the coherence in quantum computing systems. We saw this relation between the electrical voltage with the dissipative time, and yeah, there is a relation there that we can exploit to try to mitigate the error. The SEAQT modification of the equation that we use really works and can be used for simulating relaxation in NISQ devices. And the method for generating randomly perturbed density operators allows a realistic simulation of NISQ devices. And with that, I finish.
Thank you, John. Some questions, please. John, I would like to have first seen an schematic way your methodology. How is your methodology proposed to solve the problem? I didn't see it at the beginning. I suggest that you put this part in your presentation because you make the review of the state of the art and all that. But I think that I didn't see what is the methodology of your research research work. I'm going to ask you this, a kind of
Okay.
Sequence of steps that you are executing in your work.
Okay.
And also, I didn't see your schedule, your time schedule. How is it now?
Yeah, to talk about that, I am in this moment writing the thesis and also working on that last part of the project that we are doing. Also, we have some modification of the papers that we are going to publish. Then, yeah, I didn't include, but I am going to work in this period of time because I finish in next year in May for working on the thesis that I have already have something and finish the papers and this last project that is
it's
something.
very good work. But I would like to have. I'm going to ask you that send me an schedule in the time and the activities that are pending, just to control the time, the ending time.
Okay.
Please. Anybody has a question? Or some comments from the professors? Okay, Sergio, go ahead, please.
Well, I guess I could make a comment. I mean, I've been working with John now for what, going on 2 years, 2.5 years, and it's actually phenomenal, the work that he's done. I mean, considering he's a mechanical engineer and he's actually been able to for instance, work with these quantum devices and figure out how to run them on his own, right? I mean, I did not have the expertise for that, neither did Professor Cano or Asensio. And so this is really very original work on the part of John. And his plan is, as he said, to either end in May or by the end of next summer, to get the rest of this done, and I think it's a very, very original contribution to the literature.
Yes, it looks great. Thank you, Dr. Michael.
Thank you.
Sergio, do you have
Thank you, Hector. I think I agree with Professor von Stokowski. John has done a very good job, a very original one, especially on the evolution of quantum computers I only have one question for John, and a very general one. You are doing a PhD in mechanical engineering. Can you explain to the public what is the relation of your work with mechanical engineering?
Okay. Yeah. Well, I first think that this combination of the second law of thermodynamics, or the thermodynamics in general, that can explain the phenomena of quantum mechanics is really something that is useful, or have been shown useful. And yeah, I think that from that perspective makes this work suitable for someone that is working in quantum mechanical in these topics, because we can combine our knowledge in the thermodynamic point of view here in quantum mechanics, and we can make predictions. And yeah, I think that's my answer.
Okay, thank you, John.
Okay.
Thank you, Sergio. Cesar, do you have any comment?
Hi, everybody. Well, from my point of view, as Michael and Sergio says, this is a very good work, and John has worked very, very fast, and he learning quite efficiently all these hard concepts. And for other presentations, I can suggest to John to explain in a more physical way for instance, the way the free parameters are chosen in order to reproduce the experimental results, and that's all I want to say.
Okay.
Thank you very much, Cesar. Okay, if anybody wants to say something, please. Okay, thank you very much for everyone, and it's a good presentation to finish this course, and we're still in contact, and see you soon. Thank you very much.
Thank you. Bye.
Thank you. Bye.
So.
See you.
Okay, see you. Bye.
Bye.